So welcome back. This is the part 2 of massive parallel processing. MapReduce was the first generation. The IDs are going to survive, and now we're already looking at the second generation. So I'm going to show you how Apache Spark works. There's a couple of others. Of course, it's not the only one out there. So just to summarize where we are still at the processing level, right? Just a continuation of MapReduce. So now you know that MapReduce looks like this on the logical level, a map phase, followed by shuffling, followed by a reduce phase. And now you even know physically how it works on the machines with functions, tasks, slots, and so on. But there's a couple of problems with that, right? You remember also I told you slots, tasks, and so on. You know the architecture with a task tracker, job tracker. But the first thing I want to show you is that that was the first version of MapReduce in the initial form. But there's a couple of problems with this architecture, this initial architecture, is that the job tracker, which is on the same machine as the name node up there, has too much things to do. It has to manage the resources, the CPU memory, and so on, has to schedule who does the mapping, which slots map, which slots reduce. It has to monitor machines. If there's a crash, it has to detect it. It has to restart the tasks and redo the tasks if they did not succeed. It has to be fault tolerant, and so on and so on. That's a huge bunch of responsibilities on the job tracker. And in fact, it's too much. And you know, jack of all trades, master of none, right? So that as goes the saying. So we have a problem here. And because of this, there are a couple of issues. The first one is scalability. MapReduce was scaled up all the way to 4,000 nodes, but that's still not a whole data center, right? So that was the limit, and that went all the way to 4,000 tasks. It's already a lot, but still we were hitting a limit at that point. The second is, as I said, the bottleneck. The job tracker has so much to do that this is the bottleneck of the whole system. It has to both schedule the resources and monitor the resources, right, at the same time. Another problem is that the assignment of the slots, which CPU cores are responsible for mapping and which CPU cores are responsible for reducing, in that first version is decided at the beginning once and for all. So you basically tell this core you're going to map, this core you're going to reduce, and so on, statically. That means that, as you know, that reducing cannot start until the mapping is done. Only some downloads can be done, but you cannot start calling the reduce function until the mapping phase is complete. What that means concretely is that all the CPU cores that were assigned reduce responsibility, reduce slots, they have nothing to do during the whole map phase, except maybe downloading a few key value pairs eagerly, but that's it. So that's a bit of a waste of resources, right? So that's the first thing in there. We are wasting the resources on the CPUs assigned to reduce. For all these reasons, a new design was introduced that is in fact not specific to MapReduce. It's actually specific to many other paradigms for solving that problem. And it was called yet another resource negotiator. Whenever somebody starts with something starts with YA, it's probably meaning yet another, like YAML, yet another markup language, Yarn, yet another resource negotiator. Okay? So the idea, I'm not going to tell you a lot about that. I could cover hours of lectures. So just so you understand on the high level what's going on. We have yet another centralized architecture now with a resource manager and node managers. And the idea is that a little bit like Docker or like, Kubernetes and so on, I oversimplify a bit by saying that, we have some virtualization of the resources on the machines with so-called containers that have some CPUs, some allocated memory, and so on. And so what's going to happen is that a client might submit a job to the resource manager. That might be a MapReduce job, but it could actually be anything else, Spark, whatever. The resource manager is going to say, okay, fine, I'm going to help you carry out that job, but I'm not going to do it myself. I'm not going to take care of the orchestration of the job. I'm going to delegate to a container. So the resource manager assigns some resources on a machine, and one of the containers is created and promoted to being an application master. The application master is going to take care of the MapReduce job, if it's a MapReduce job. In other words, the application master is going to do what the job tracker used to do in terms of fault tolerance and restarting the map tasks or the reduced tasks that didn't succeed and so on. So you see that that's a shift, because in MapReduce version 1, it was all done here. What's happening now is we delegate the part of orchestrating the job down there, right? So this application master takes control and is going to be responsible of the MapReduce job, but then he's going to say, okay, now I need resources. I'm not going to do the MapReduce job on my own. I need map slots and I need reduce slots. So the application master connects back to the resource manager and say, please, I need help, allocate machines for me. So the resource manager says, okay, fine, here are these slots. Since for now, I'm just mapping, I only need the mapping slots. So I'm basically given a few mapping slots in here and I can start mapping, right? So now you see, this is out of the picture now, right? This is acting as the job tracker. These are acting as the task trackers doing just mapping. When the mapping phase is done, the application master can connect back to the resource manager, request more slots for doing the reducing, and then dynamically new containers will be allocated for the reducing phase. So you see, it's more flexible. First, delegate it to the application master. Second, dynamic allocation of containers based on what you need, right? So it's a better use of resources. What's more, you can have multiple application masters. On the same cluster of machines, you might have 3 MapReduce jobs running at the same time. They will each have their own application master. You might have, even at the same time, 3 MapReduce jobs, 6 Apache Sparks jobs, maybe somebody else with MPI, message parsing interface, and so on, because often a cluster is used by plenty of people, right? And now we have the flexibility to do that. We can have a cluster used by plenty of people with this mechanism to allocate resources based on everybody's needs. This is Yarn. And so the idea is really that the resource manager just schedules and allocates the containers, and that's it. All the rest, the monitoring and something specific to MapReduce and so on, that's now the application master, right? So these containers are basically allocated with a specific quantity of memory and a specific number of CPU cores. It is ongoing work that to also try to consider some disk space or disk reading bandwidth capacity or network bandwidth and so on. But so far, the focus has been a lot on memory and CPU. These are really the two that where the attention is focused, right? So you basically say, I want, for example, 10 containers with 2 cores and 10 gigabytes each of memory, right? That could be a way of defining the containers. So now, and this is where I'm not entering any details, I squeezed that down to just one slide, to be a bit more, especially at the master's level, is the resource manager schedules the cluster for maybe there are 10 different people using it. So it distributes the resources among these people, and everybody is doing their own MapReduce job, scheduled nicely and organized based on imagine the departments at ETH that have a cluster, maybe depending on their contributions, they get more or less of the percentage of the cluster, right? However, the resource manager couldn't care less if your job fails. That's not its problem. That's the problem of the application master, right? It's only there to schedule and allocate the resources. Then, the monitoring is done with a way similar with its heartbeats, right? Similar to HDFS, where you keep track of the nodes that are still alive. So that the resource manager can do because it needs to know how many CPUs and how much memory is available. But the monitoring of whether a map task is successful or not, that is done by the application master, right? So the application master, one of many, there could be multiple applications master, but the application master monitors the containers that it has requested. If a map task fails, it's going to relaunch it, maybe request new containers and so on, right? So again, separation between the scheduling and the monitoring. Then we have better scalability. In fact, I don't know no, I don't have it here. Now we can do it on 10,000 nodes and 100,000 map tasks. So that's a better scale up. It's also more available, and multi-tenancy, because again, you can use the cluster with other people, right? And in fact, a lot of companies for them, it doesn't matter how fast you can execute your job. It matters that the cluster is efficiently used across your company. You don't want the cluster to be idle or underutilized and so on. So the focus at the company level is the multi-tenancy and fair allocation of resources, right? That's something that many people forget about Spark and MapReduce, because when you just play around with it, you basically trigger a few machines on Amazon and it looks like you're the only one. But in a company, you have other people using the cluster at the same time as you. Right. So that is Yarn. That's the quick intro I wanted to give on Yarn. And now there is a second version of MapReduce that is built on Yarn, but the idea is exactly the same. The map task, map slots, and so works exactly in the same way, apart from the fact that there's the delegation of the whole tracking to a machine on one of the worker nodes and no longer on the coordinator node. Turns out that Spark will also be implemented on Yarn in exactly the same way. So now, quick intro to Spark in the few minutes that I have left. I'll start with MapReduce. So MapReduce, very, very coarsely, can be seen as a parallel face followed by shuffling, followed by a parallel face. If I want to push it a little bit, it's basically map, shuffle, map. Because if you think of it, reduce and map, it's kind of similar in the way that it just treats data in parallel. But the problem is that there's only one shuffle. What if you want map, shuffle, map, shuffle, map, shuffle, map, shuffle, map, shuffle, map, like something more general than that? Spark MapReduce cannot do that. You would need multiple MapReduce jobs, which is complex to organize. So MapReduce only really supports this very highly specific scenario where you have an input data that you map to intermediate data that you reduce to output data. Spark does that. Basically generalize that you're no longer constrained to just map and reduce. Now you can have a fully general architecture of collections connected in a general way, just no cycles. That's all, for obvious reasons, because you cannot go back to the past. But now you can do it in a fully generic way. That's the first thing. The second thing is that it doesn't require for collections to be key value pairs. Now you can have collections of whatever, even if it's not pairs. Collections of integers, collections of strings, collections of JSON objects, collections of pairs if you want, right? But it doesn't have to be pairs. And third, not just map or reduce, you can have a catalog of like 100 different things you can do beyond just map and reduce. This is basically the difference. There's a name for these blue rectangles, right? So in MapReduce, we call them input collection of key value pairs, intermediate collection of key value pairs, and output collection of key value pairs. In Spark, there are so many of them that we needed to give them a generic name, and that generic name is RDD. Resilient Distributed Data Sets. An RDD is just a collection of whatever, a collection of values. A huge collection of values could be a collection of 1 billion whatevers, integers, dates, objects, whatever you want. And because it's billions of them, it's a big collection. We are going to partition it. All of these values that you have in your collection are spread all over the machines. Just like in MapReduce, in fact, the collections of key value pairs are also spread all over the machines. So that's the D, the first D is distributed, and that means that it's partitioned all over the cluster. That's the first thing. Resilience means that if at some point we lose part of it or we deleted it and so on, it's no big deal. You can just recompute it and reconstruct it on the fly and get it back. So it's resilient, right? And data set, well, just a collection of whatever, so that's basically data. Okay, so that's an RDD. Who is with me? Right? And then what do you do with RDDs? Well, you can create them. For example, you can create an RDD out of some HDFS files, or you can create it from S3. You can create it from your local file system. That works too for small amounts of data, or on the fly. You can have, for example, a list in Python, and you want to say, okay, make that list an RDD, ship it over to the Spark cluster, and then work in parallel on it. So you can create them. You can transform them. Map and reduce are just two ways you can do that, but we'll see it's hundreds of ways you can transform things in there. It's a full restaurant menu to pick from. And finally, an action, that's when you're done, you have computed your output. Now, you can show it on your screen if it's small enough in your Jupyter notebook, or you can write it down back to S3, or you can write it back to HDFS, or if it's small enough, you can download it to your laptop, right? So you can create RDDs, you can transform RDDs into other RDDs, and you can output your RDD to the disk, to your laptop, or to your screen. Okay, so that's basically it. So I think I should stop here to not start talking about something else. But again, if I summarize, Spark is the next generation of MapReduce. It doesn't have to be pairs of key values anymore, can be collections of anything. It doesn't have to be just two phases, map and reduce. Now you can have a fully generic chain of transformations. And it's not just map and reduce. You now have dozens, if not hundreds of ways that you can transform the data. After the Easter vacations, I'm going to show you some of these transformations. I'm going to show you examples. And you will see that this is basically a better MapReduce. That takes it to the next level and also easier to use. You can very easily write in a Jupyter notebook in Python, use Spark. You might have heard of PySpark. So that's it for this week. There are no exercises, right, this week, because Friday would be a holiday. And so we just said, okay, the whole week there's no exercise. And then we are all back in 2 weeks. So there's no lecture next week. That's the no teaching week at ETH. And then I'll see you again in 2 weeks. And then there will be exercises again in 2 weeks, right? So thank you very much for attending this lecture. If you have any questions, send them my way via Moodle, via emails, via the Element chat. Enjoy your Easter holidays. Take some time to take a break, also for your brain. And I'll see you in 2 weeks. Thank you very much.